Good afternoon, everybody. Welcome to the colloquium this week, the colloquium of the C3.ai Digital Transformation Institute. I'll just tell you a little bit about the Institute before we get started with the talk. It's the mission of the Institute to help develop this new and emerging field of digital transformation and the science and technology underpinnings for this application to all kinds of areas: energy, transportation, healthcare. And it's a partnership. The supporters are C3.ai and Microsoft. It's co-located at the University of Illinois Urbana-Champaign and at Berkeley. And the co-lead institutions and the partners are Carnegie Mellon, KTH, Stockholm, our most recent member, the Lawrence Berkeley National Labs, MIT, the National Center for Supercomputing and Applications at the University of Illinois, Princeton, Stanford, and the University of Chicago. So just to give you a little bit of a preview of the upcoming talks, next week, Steph Bertozzi and Juan Pablo Gutierrez will talk about how they've been using the data lake, the C3.ai data lake, to understand the spread and transmission of COVID in Mexico. Zico Colte from Carnegie Mellon will talk about equilibrium approaches to deep learning. Anna Houghton and Jonathan Ozick from the University of Chicago will talk about the social determinants of the spread of COVID and how to address its disproportionate effect on communities of color. Matis Teglarski will talk about mathematical aspects of deep learning. And this has been a bit of a theme. We had talks by René Vidal and Yi Ma, and even last week 2 weeks ago, by Alexander Madry on the mathematical aspects of deep learning and this emerging, wonderful, rich theory. Even actually Baranyuk's talk last week was also on this topic. Divakar Shukla, University of Illinois, will talk about the mechanism for attachment of the virus and its spikes. Christian Borks from Berkeley will talk about network science and dynamic learning. Nathan Srebro will talk as continued about this mathematics of deep learning through optimization. Stefana Parasco from Princeton will talk about an architect's view to how you actually bring the social distancing using light, how you make it happen. Stefano Suato from UCLA and Amazon will talk about differential learning, and Jeff Sharma from the University of Illinois will talk about learning. And the series actually continues through June, but I won't be able to stop it at that point. The presentations, the repository presentations are on the YouTube. They're accessible through the website, but that's sort of what the YouTube video looks like. I want to be sure to bring to your notice that we have a second call for projects on digital transformation and AI for energy and climate security. And this has been in the press a lot. Last week in the New York Times, a wonderful op-ed by Arun Majumdar at Stanford and Bill Collins here and other co-authors, Bill Collins at Lawrence Berkeley Labs, on really about using AI to predict when events like the ones in Texas would happen. This is this item 10 here, AI for improved natural catastrophe risk assessment. And then there's other topics that have been showing up about using AI for new materials design for carbon sequestration. So we'd love to see topics in all of this, energy markets, how not to spike prices. All of those are certainly fair game here. We have a continuing sequence of webinars, and they are continuing as well this month. Proposals are due March 29th, and so let's get on to today's talk. And the main feature here is Lillian. And, there's a Q&A feature to ask questions, upvote them, all of that. Larry will please look out. Larry Rohrbach will be the moderator, and you are in for a lovely talk today. I must have seen a preview of it, but It's called Beyond Open Loop Thinking, a prelude to learning-based systems. I won't, so I'll leave the suspense there. Let me tell you a little bit about Lillian. So Lillian came to Berkeley from University of Nevada, Las Vegas, and she'd done math and EECS, and she's now at the University of Washington. And her interests lie at the intersection of learning, optimization, game theory, economics, network games. And she has already in her short career at the University of Washington, she has had a huge number of research awards, the NSF Career Award, the Office of Naval Research, ONR Young Investigator Award, and the Dhanani Faculty Fellowship. So it is a great pleasure. I am going to mute myself and I will relinquish the screen to you, Lillian. The floor is yours.
Okay.
You see your slides.
Okay, excellent. So thank you for that introduction. So as suggested, I'm going to talk about something I've been thinking about quite a bit over the last couple of years, and in particular over the last few months, related to how to go beyond sort of open loop thinking and designing learning algorithms for intelligent systems. So I'll start with a little vignette to sort of place some of the work in the context of things that we can relate to on a daily basis. So imagine that you're going to go to some online marketplace like Amazon to order, say, some cat treats for your cat. And so what you do is you go and you search, and you're going to interact with some ranking and pricing algorithms that are going to decide what to present to you and what price based on, say, past interactions or other searches by other people. So then once you place your order, it's going to get passed along to a distribution and routing phase where some optimization or resource allocation algorithms make decisions about which warehouse has the item and which one is closest to you. Then the order will get passed along to a courier market where maybe a matching algorithm decides which courier is going to take the item to your house. Then the courier navigates to your front door and perhaps participates in a curbside market, such as an auction, or even just engaging with pricing algorithms to procure some curb space. Then your cat eats these treats, and you provide some feedback in the form of, say, a product review, which then sort of revises the sort of data and information that the online marketplace has to determine the next sort of interaction that you'll have with it. So what we have here is a sort of complex market ecosystem in which you have algorithms that are interacting with each other, and outputs from one algorithm feed in as inputs to another. And so when we see these in practice, they seem to work well, this sort of system. I mean, we've seen this over the course of the pandemic, where we can engage with Amazon and order lots of things to our house without having to leave. But in reality, there's often sort of unintended consequences that can emerge. And so I'll just highlight one here. So recently we saw this sort of phenomena with the GameStop stock. And so what happened here is that you have, on the one side, you have sort of like positive collusion that's happening among small players that are now able to engage in the market through apps like Robinhood or eToro, or there's a number of them now, and be able to participate as buyers in this sort of stock market. And so they sort of took advantage of a situation in which these large hedge funds were shorting on a stock they were betting would go down. And so on the other side, you have like sort of negative collusion amongst these hedge funds who are then trying to stop these small players from sort of taking advantage of this sort of loophole, if you will, in the market that the hedge funds were taking advantage of. And so what we saw is like extremely volatile prices related to GameStop, and this sort of percolated outwards to other parts of the stock market due to the sort of shorting mechanism that was trying to be exploited by the hedge funds. So this is an interesting unintended consequence of now being able to trade at high speed and small players being able to engage in the market. So if we go back to our picture of this sort of market ecosystem, if we think about even training one of these algorithms, the way that we do it is also in sort of a market ecosystem, but of a different nature. So essentially what we have is we have some training phase in which we have sort of this meta learning combined with some, say, gradient-based algorithm for training our algorithms. Once we get an output of this training phase, it then gets fed into, say, an evaluation phase where it's pitted against other algorithms, say in a test suite. And so we end up with algorithms interacting and we get very complex dynamics that we don't necessarily understand. Some algorithm is chosen based on evaluation criteria and deployed in practice. And then what we get is a sort of, the algorithm changes the environment, and then we get observation of this changed environment, which then feed back into the training phase. So there's various different difficult problems that I've highlighted here on this slide. And in today's talk, I'll just focus on this one at the bottom. So this feedback-induced distributional shift. And so what I want to pose is this sort of point that I mentioned in the abstract of my talk, which actually came out of an email exchange with Shankar. It made me really revisit and think some of the things I was thinking about. And essentially, it's this central tenet that we have for present day machine learning, which is that if a phenomena is hard to model, then we sort of just assume that we can take samples from the world, and those are going to be representative of some static or otherwise independent distribution. And while this might be true in many situations, I would argue that it's not the case in many large-scale intelligent systems, in particular infrastructure systems that we sort of depend on. And so let me give some examples of challenges that arise. So the first is really the fact that you can have a distributional shift in bias that results because our algorithms tend to be trained on past data without taking into consideration that the algorithm itself may impact or change the environment. So let me give some examples of this. So the first is curbside management. So this is something that I work on that I think is pretty fascinating. And the reason is that it turns out that curbside usage is really a linchpin for various different aspects of the way a city runs. So this includes business district vitality, whether you can procure a construction permit or not, whether residents are able to take advantage of curb usage around their homes. All of these things are important aspects that poorly mismanaged curbside system, poorly managed parking system, for instance, can cause negative consequences for. And so basically in practice, what happens is that cities go and they collect ground truth based on manual studies. They walk around and they collect data to create a model that they then use to set policy. And the issue is that they tend, due to like resource constraints, they tend to do this, say, one time a year. And if you look at this data at the bottom, so this is real data from Seattle. And so basically what it's showing is that the time of day and day of week is highly influential on the sort of parking distribution. And similarly, other external contexts like whether it's raining or not tends to be extremely important as to how the parking or curbside usage is. And so if you go and collect data on one day, then of course it's going to be biased to whatever the environmental context was of that day. Nonetheless, this is sort of how prices are, policy is set. A second, maybe more important application is this predictive policing. So there was a study in 2016, which is cited here at the bottom, published in the Royal Statistical Society, which looked at Oakland. And so on the left, what you see in the top box plot is actual drug arrests from 2010. And you see that they're concentrated in West Oakland there around International Boulevard. And in the bottom, you actually have estimated drug use from 2011 health survey. And you can see that self-reported drug use is pretty widespread across Oakland. It's not necessarily concentrated where the drug arrests are. And so in this study, what they did is they used Predpol, which is one of the predominant predictive policing algorithms, to do day-ahead hotspot prediction. So essentially, it predicts where police should go the next day. And so maybe not surprisingly, what it did is, based on the data that it has, is just keep predicting this area in Oakland, in West Oakland. And so basically what's happening is you're reinforcing the biases. So the more that you go there to collect data, the more frequently you're going to find crime, for instance. And so this is particularly a negative thing because it's impacting certain races of people. So if you look on the right here, we have at the top the actual data for police targeting for drugs by race, and you see people of color are predominantly targeted, while the estimated drug use by race tends to lean towards people not of color. And so, you know, this is this sort of ignoring this feedback loop that's actually happening in collecting these this data in terms of like where to go and police is having extremely negative consequences for various different socioeconomic groups. Okay, second is sort of challenge I want to point out is that many times when we're training algorithms, whether online or online, or offline or online, the data that we have from these systems tends to be from human users, which may be strategic in how they provide data. So again, I'll give a couple examples. So the first is this Surge Club. So in 2019, it was reported that Uber drivers were trying to trigger, and successfully doing so, surge prices because they felt unfairly treated by the company. And so what they do is they go to like an airport and they all turn off their phone. So they induce an artificial drop in supply, and then the pricing algorithm will trigger a surge, and then they'll turn on their app so they get the higher price. So they're specifically manipulating the pricing algorithm by changing how they report their location and availability. And this price increase, sadly, it doesn't get offloaded onto the platform as is their sort of target, but offloaded onto the demand side of the market. So this has really negative consequences for both sides of the market in this particular case. A second is related to this contact tracing. So early in the pandemic, there was a lot of push for having digital contact tracing apps. And so quickly it was discovered that these apps, if only a small proportion of users actually use them, they're at best worthless, and at worst, they can be potentially harmful and actually instill a false sense of security in the user population. And so what can happen is that if a user is using this app, they may be concerned if you can even encourage them to use it in the first place, if they're only marginally care about their privacy. Then what they might do is just selectively report where they've been, as this sort of cartoon on the right sort of indicates. So then again, you have this sort of biased data on which you're trying to make policy decisions. Okay, so I've given several examples. And so what I want to do in today's talk is think about how we can design learning algorithms, decision-making algorithms, given that we're going to take into consideration that you might have decision-dependent data distributions, as well as strategically generated data. So specifically, I'd like to go beyond this sort of optimization view of training machine learning algorithms, where we think about minimizing a loss, and instead try to use the language of game theory to capture these fundamental phenomena that I've described in the previous slides. And so what we'll see is that there's actually a lot of rich literature already that we can just sort of marry together in order to get what I would like to say is a reasonable abstraction of these problems. So I'll describe that, and then in terms of the results that I'll give, I'll first take a step back and just try to give very strong results for first order methods, something that we can actually implement, something that will be scalable. And then once we see that we can obtain some nice convergence guarantees, theoretical guarantees for simple algorithms, simple sample efficient algorithms, then what we'll do is take a small step forward. And I'll describe a little bit about what we've been doing towards trying to model this problem of learning with decision-dependent data. And this is completely preliminary work. So I'm just hoping there's a lot more questions than there is answers here. All right. So let's start with the sort of game theoretic abstraction. So what we have is we have some machine learning algorithm, which I'll just call learner here. And it's parameterized by theta. So we want to try to design this theta by minimizing a loss function, described here as L. But the challenge is that the data that the loss depends on, Z here, is sampled from a distribution that actually depends on theta as well. So this is different than the classical, say, empirical risk minimization or risk minimization you might see in traditional machine learning. And in addition, we want to take into consideration that maybe this decision-dependent distribution, the model that we have for it, may be misspecified, that we're going to allow for some error. So we want to be robust to this. So then we incorporate this sort of distribution class over which we allow our distribution mu, decision-dependent distribution mu to vary. And then finally, we want to choose this theta in order to minimize this quantity. So this is sort of the general abstraction that we'll take a look at in today's talk. And so let me just point out that this is not new. So first of all, if we ignore the distributional robust part of the problem, then this problem has long been studied in stochastic programming in the OR literature under the name decision-dependent probabilities or decision-dependent data. And so there's a nice review paper from 2018 that covers a lot of this older literature. And basically the problems that were being studied there are what are known as discrete choice models or other highly resource constrained problems where you typically model them as integer program. And so the focus was more on that style of problem. More recently, we've seen a lot of work from the convex optimization community and machine learning community revisiting this problem from the perspective of, from this sort of machine learning perspective. And so the most recent literature that is relevant here is from the machine learning community, where they refer to this problem as performative prediction. And I think this sort of emerged out of thinking about problems related to strategic classification. So in short, this formulation of thinking about decision-dependent distributions is not new in itself. On the other side of the coin, thinking about if we ignore the decision-dependent data, then distributionally robust optimization essentially captures the other sort of problem. And so this has also been studied quite a bit, and I've cited here a recent survey that covers a number of different formulations that's worth taking a look at if there's interest. And so essentially what we're going to do, and the abstraction I presented on the previous slide is sort of a marriage of these two things. What we're going to try to do is leverage game theoretic tools in order to design more efficient algorithms that can handle this type of problem. Okay, so as I mentioned, I'll start by taking a little step back and try to understand something very fundamental just about the min-max problem itself. So we'll just think about min-max problems. And the reason is that they sort of not only show up in this abstraction that I just mentioned, but also in a number of other recent formulations of machine learning algorithms, including adversarial learning, hyperparameter tuning, and so on and so forth. And so this game theoretic abstraction sort of lends this new perspective on how we should view machine learning, the design of machine learning algorithms in some sense. And so the challenge is that there's really this significant gap between theory and practice. In particular, we don't have good theoretical guarantees for things, heuristics that seem to work well in practice, in particular for first order methods. So what I'd like to do is try to talk a little bit about what we're doing to close this gap between theory and practice, and then we'll come back to this more abstract decision-dependent, learning with decision-dependent data problem. So the formulation here is that we have a zero-sum game defined by a sufficiently smooth cost function f. And you can think about the corresponding min-max problem, where player 1 is minimizing with respect to x1, player 2 maximizing with respect to x2. And the most natural, arguably, learning dynamic in the setting is just gradient descent ascent, where here I've allowed for the players to have different learning rates, gamma 1 and gamma 2. So in doing so, we can introduce this timescale separation parameter tau, which is the ratio of gamma 2 to gamma 1. And so on the theoretical side, what we know for these sort of min-max problems, or Stackelberg games, as they've also been referred to, is that we can get provable convergence to game theoretically meaningful equilibria if we use second order information. And so essentially what's happening here is you view the maximizing from the perspective of the minimizing player, you view the maximizing player as playing a best response. And then you sort of get this implicit map from x1 to x2 that can then be used to generate sort of these second order updates where you differentiate through this implicit map. And so it's been shown that those work well in terms of getting provable convergence. On the other hand, in practice, people don't usually implement these second order methods because they can take a lot of samples to be able to estimate these higher order gradients. So instead, they use first order methods with this timescale separation, which approximates sort of this hierarchical structure. And this is shown to work really well in adversarial learning and even in actor-critic versions of reinforcement learning that are viewed with this hierarchical structure as well. So we want to close this gap between theory and practice. So let me start with what is known. So on the left here, for first order methods with no timescale separation, we know there are spurious stable attractors, critical points that are not game theoretically meaningful. And we know that there are game theoretically meaningful points, strict local min-max, that are not stable. So people have constructed nice little toy examples of this that show both of these cases. On the other end of the spectrum, when we take tau to infinity, it was recently shown by Chi-Jin and colleagues, and is also known in this in a different context in the singular perturbation literature, that there's an equivalence between these strict local min-max points and locally stable points. So the problem with this is it requires your timescale separation to go off to infinity, and that leads to numerical issues. And so you don't really have a practically implementable scheme in many cases. So what we want to do is sort of fill in this gap in the middle and say, okay, can we come up with a non-asymptotic construction of this, of a finite timescale separation such that we get the equivalence between game theoretically meaningful points and stable attractors, the critical points of the dynamics. So the way that we study this problem is by viewing it as a dynamical system. So we have this sort of simple discrete time dynamical system in the blue box here, where we have two key parameters, gamma 1 here, which is the step size, and then tau, which is a timescale separation parameter. To separate the effects of those, we take gamma 1 in the limit. So we get this continuous time dynamical system on the right, which only depends now on the parameter tau. And then once we understand stability in terms of tau, we can go back to the discrete time system. And the way that we understand stability is by looking at the local linearization of this continuous time dynamical system. So now we should understand what sorts of points that, like how to characterize the equilibrium points that we would like to prove convergence to. So the class of equilibria that I'll talk about are these local Stackelberg equilibria, or min-max points. And so I've written it here specifically in this optimization framework because I want to motivate the conditions at the bottom that define this differential Stackelberg. So essentially what's happening is the first player is optimizing, taking into consideration that the second player is best responding. And the second player is just myopically best responding. So if we write down the first and second order sufficient conditions for this optimization problem, we get what's in this blue box at the bottom. And this defines a differential Stackelberg or a strict local min-max. And so the interesting thing here, if we think back to our continuous time dynamical system, and we look at the local linearization of this dynamical system, it defines what's called the Gamg Jacobian. And all of the information that we need to characterize this differential Stackelberg is in, at least in terms of the second order conditions, is inside this sort of Gamg Jacobian matrix. So in particular, we'll say that a differential Stackelberg equilibrium is a point such that its G maps to 0, so the individual gradients are 0, and the Schur complement of this Gamg Jacobian is positive definite. So that's the second order sufficient conditions for this first optimization problem. And the second player's individual Hessian is positive definite. So that would be the second order conditions for this second player's best response problem. And so we want to compare these differential Stackelberg to points that are stable points for the dynamics, which are going to be points such that the spectrum of this Gamg Jacobian or in the negative of this Gamg Jacobian are in the open left half plane. Okay. So now going back to the problem at hand, we want to close this gap between theory and practice. And so to motivate that we can do this by constructing a finite value of tau in a non-asymptotic way, I want to talk about the asymptotic, what's happening in the asymptotic case. So what happens is the spectrum of J tau, what it does is it splits into two pieces asymptotically. one is approaching one component of the spectrum is approaching the spectrum of the Schur complement, and the other is approaching at a linear rate the individual Hessian of the second player. So this is why you should expect, as you scale tau to infinity, that basically the stability properties of the dynamical system are approaching the second order sufficient conditions for the differential Stackelberg equilibrium. But if we take a look at this little example at the bottom here, it's just a quadratic game. 0, 0 is a strict local min-max for this game. And if we look in the right plot here, we're basically looking at what happens to the eigenvalues as we scale tau. So this is the blue thing is the blue part is the open left half plane. And so what you see is that the system starts unstable. So we have 2 eigenvalues in the open right half plane. And then as we scale tau, when it hits 2, so that's when you see those red stars, suddenly the eigenvalues cross into the open left half plane. And it's stable thereafter. And this happens well before the asymptotic splitting, which is occurring when you see the eigenvalues collapse on the real line and move in opposite directions. So this suggests that we should be able to, at least by example, should be able to come up with a non-asymptotic construction. So I won't go into details of this, but I'll just give you the result. So what we can show is that we can give provable local convergence in the sense that that there exists this lower bound on the timescale separation, so tau star here, such that we have equivalence between the stable points for all larger tau and the game theoretically meaningful points, these differential Stackelberg. But more importantly, we can come up with a non-asymptotic construction. And the way that we do this is use this like old tool from control theory called a guard map. It's basically a polynomial that acts as a certificate for precisely when the eigenvalues of j tau minus j tau move from the open right half plane to the open left half plane. And using some clever algebraic tools, we can reduce this polynomial into the form that you see at the bottom here, which is a little bit hard to parse, but the important thing is this piece on the right, which is just an eigenvalue problem in tau. So we can construct tau by solving this eigenvalue problem. And the matrix B here only depends on the block components of the game Jacobian here. So which turns out that this construction is tight, and we get an efficient computation using, again, some clever algebraic tools that reduce these Kronecker sums that you see to what's known as a block Kronecker sum that essentially removes redundancies in symmetric matrices. Okay, so we have this result. How do we use it? Why is this interesting? So essentially what we can do is we can construct tau for whole classes of games. And this leads to relaxed assumptions on problems of interest in terms of getting convergence guarantees. So the first class of problems of interest are these adversarial learning problems known as generative adversarial networks. And so what we can show is that for GANs that satisfy this realizable assumption, or relaxed realizable assumption, which is, as far as I know, the least restrictive assumptions we have on the GAN problem such that we get provable, or we have any theoretical guarantees. And what it means is essentially the generator is able to reconstruct the original distribution. And so for this class, we can show that the lower bound on timescale separation is actually 0. So that means we can train our GAN for any tau greater than timescale separation greater than 0 and still get provable convergence. So the benefit of this is that methods that theoretical guarantees in practice are predominantly of this flavor of a 2 timescale stochastic approximation update, which requires this asymptotic relationship between the step size sequence for the first player and the second player. And it ends up leading to a situation when you actually implement this such that the second player, which is the discriminator in this case, equilibrates too fast and doesn't make progress. So no one implements those. They tend to do these other heuristics using timescale separation. And so our results actually put some theoretical backing to that. The second class is perhaps a little bit more relevant for the original problem posed at the beginning of this talk. And so essentially what we can show is that for this class of non-convex mu-PL games, we can also characterize the lower bound on timescale separation. So these non-convex mu-PL games are such that F is non-convex in X1, but is mu-PL in x2. And what that means is that the gradient for the second player grows as a quadratic function of the suboptimalities. This is essentially a relaxation of being concave in x2. And so there's a number of machine learning problems that are posed in the context of either non-convex mu-PL games or non-convex concave games. And so I've listed a handful of these here at the bottom. But this is one of the main classes that people tend to look at, for example, in adversarial learning or even in, say, fair classification. And so what we can show for this, I'll just quickly go through these results. Essentially, what we can show for this entire class is that, first of all, you cannot have spurious stable points. That means that it's not possible that you have a critical point that's not a game, theoretically, a differential Stackelberg that's stable. Moreover, any differential Stackelberg is going to be stable for all tau larger than the first tau for which it's stable. And that tau for which it's stable is always guaranteed to exist. So what this means in practice is if independent of the critical points, I don't need to know anything about them. If I fix a tau, then all of the stable points of T-GDA are going to be strict local min-max if such a stable point exists. And then no new spurious points can be introduced as I scale tau up. And so more importantly, we can actually construct a potential function for this class of games, which means that you don't even have limit cycles or any of this other more complex behavior that people have been discovering in training, for example, GANs and some other adversarial learning problems. And so combining this with an avoidance of saddle, an asymptotic avoidance of saddle result, we essentially get a provable convergence, a global convergence guarantee for the T-GDA update to the set of differential Stackelberg equilibria. So the importance of this is that in many of these min-max formulations of machine learning problems, people tend to implement things like the zeroth order or other black box. This is particularly true in adversarial learning. These sort of black box type updates, but they only get convergence to epsilon stationary points. And so this could actually be something like a local max for the minimizing player. And instead, what we do is we can leverage this result to give provable convergence to strict local min-max. All right, so I'll just summarize this sort of section by saying what are the sort of important takeaways here. So first of all, in modeling machine learning problems in which the data might be generated adversarially, these game theoretic abstractions can be highly beneficial. Moreover, we can leverage the game theoretic abstraction, in particular, the sort of hierarchical structure between these decision-making agents in this model, in order to give provable convergence guarantees to interpretable equilibria. And so I think the sort of importance here is that we took a step back and we sort of tried to analyze these first order methods so that we could give provable convergence guarantees to things, to equilibria that are game theoretically meaningful, have some interpretation. And the importance here is really that ultimately we want to solve a more complex problem, in particular this decision-dependent min-max problem. And so having a efficient first order method that's easily implementable will be beneficial when we move to that more complex setting. So now what I'd like to do is talk about this small step forward towards addressing the problem posed at the beginning. So what we've been working on recently is thinking about how to actually solve a decision-dependent distributionally robust optimization problem. And this is joint work with the students shown here at the bottom. So let's revisit the original problem. So essentially we had this decision-dependent min-max problem, if you will. The applications really are many. So at the beginning, I motivated the talk with some predictive policing. And so here you can think about the discovery, say, of crime in a particular neighborhood as being your observation yi here. And of course, it's going to be dependent on your actions that you're taking, so where you're looking. Similarly, you can think about strategic classification. So whether this is with respect to loan approval, interest rate approval, getting into a particular college. Each of these types of classification problems can be thought of in this context, in the context of the problem at the top, where the data that's being generated here might be users' features, and they're able to manipulate them in order to try to ensure that they're being positively classified. At the same time, or in other applications, you might have similar strategic manipulation, such as the contact tracing at the beginning, or even the supply and demand in the rideshare market, where users are sort of artificially manipulating their locations in the respective application domains. Okay, so let's start from one of these sort of more practical problems, let's say this rideshare problem, and see how we can actually abstract it into this theoretical or game theoretic abstraction that I showed on the previous slide. So suppose here that the features xi theta are those reported by the user, and that their true features are some, say, fixed xi bar in some fixed nominal distribution. And then we can think of mu of theta here, so the induced distribution on data points, as being induced by the mapping from the true features to this reported features, xi theta. And as an example of how this might occur, you can envision that, say, your driver who's participating in a rideshare market is maximizing their profit for the day or their revenue for the day in the form of this utility maximization model here. And so they're trying to determine what is the features I should report, meaning the location that I should report, or my availability that I should report to the platform, given that I have some understanding of what their pricing mechanism is, in order to ensure that I'm maximizing my revenue. And so this sort of abstraction captures, can be captured in the min-max formulation on the previous slide. In particular, when we think about the fact that this best response model might be wrong. So it might not be precisely the case that the way that users are behaving in practice is according to this induced distribution that we get mu theta. Okay, so if we add a little bit of structure to the problem, so that the general framework, then we can actually get something that's approaching a solvable problem. So what we've been doing is recently is looking at this variant of the problem, which we'll call the Wasserstein decision-dependent distributionally robust optimization problem, which is an entire mouthful. And essentially, the two sort of changes that we've made are, first of all, we're assuming that our loss function is going to be some generalized linear model, which captures a lot of different learning frameworks. And second, we're going to allow sort of our model misspecification, if you will, to be captured through this ambiguity set, which is essentially a delta ball in the Wasserstein distance around the empirical distribution that the learner will observe through the reported data. Okay, so first, let me tell you what is known when we actually know or don't have the distribution depending on theta. So what we know in that case is that if you have some nice structure on your loss function, then you can basically reparameterize this problem into the following min-max problem that's given here in the center. So this was actually shown in the case when phi here, the loss is just a logistic regression in this 2015 paper cited here. And so what they do is they actually reformulate even this min-max problem to a single optimization problem and then show that they can solve this for logistic regression. In a very promising recent result by Yu et al. Cited here at the bottom. Actually, these are Berkeley folks. They actually left this, first of all, they generalized the logistic regression to a generalized linear model. And then they left the problem in the min-max formulation. And then they exploit the min-max structure using extra gradient methods with some random reshuffling to get extremely fast convergence. So the interesting thing here is that they're able to leverage this min-max structure in fact, this game theoretic structure to get much faster convergence than you would get otherwise. So this is basically what's known so far. So essentially what we do is that we exploit the same trick to handle the case where we actually have decision-dependent data. So notice the feature, the difference here is these feature vectors now and the labels actually depend on theta. So the problem now is whether or not this problem is even solvable or if it's convex concave. because we don't really have any assumptions so far on how this xi is generated. So if we add some assumptions on how our data is generated, then we can actually show this problem is convex concave. So in a recent paper by Dong et al. In 2017 on strategic classification from the perspective of taking an optimization perspective, essentially they showed that if you have the best response model given at the top, with this cost function here being convex, positive homogeneous, and so on, then the best response map actually is convex. And then in your optimization problem, you're essentially just composing convex function with convex function. So then at the end of the day, we get this decision-dependent distributionally robust problem is in fact convex concave. So one of the interesting things I'll point out here, though, is that the sort of hidden here is this interaction between the learner and each user, which is itself a Stackelberg game. So this sort of begs some interesting questions related to incentive design. So suppose we want to impose extra conditions on this problem such that it's individually rational and incentive compatible and so on. So this leads to some open questions that really haven't been addressed in this domain. So sort of how do we bring together those sorts of guarantees that we would want in the design of mechanisms, so in mechanism design, together with sort of this learning with decision-dependent data, in particular strategic data. Okay, so I'm getting a little short on time here. So I'll just quickly show you a couple examples of implementing this on some real data. So essentially what we did is we took this Portuguese bank data for getting people to purchase a term deposit. So essentially they put their money in something like a CD, which is just a fixed term investment. And so there's some subset of features in this data that they can manipulate, and there's some non-manipulable features. So the non-manipulable features relate to the campaign type, marketing campaign type, and like some exogenous economic indices from Portugal. And so what we can show is that, you know, if you run the vanilla problem, it turns out that the sort of most important features of the top 20, the majority of them are actually things that are manipulable. So those are highlighted here in red. So then if we simulate the strategic behavior, so what we do is we assume this nice best response model here at the top, where we have a 2-norm cost for deviating from the true feature vectors, and it's weighted by 1/2 epsilon here. That epsilon basically determines how much this agent is going to perturb from their true features, as indicated here in this best response update. And so what we do is we solve the performative prediction problem. So this doesn't include the robustness, as well as our formulated problem here. And we actually exploit timescale separation to get faster convergence, which I won't have time to get into. But if we run simulations where we take the real data as the true feature vectors and then simulate perturbing it, then what we can show is that, of course, the distributionally robust version has this nice property that the accuracy decays much slower as you increase the size of the perturbation. So essentially, like in this plot on the right, we're training with a particular epsilon, and then we're perturbing it with a much larger value of epsilon and seeing how the accuracy degrades over time. And you can see, yeah, that, I mean, the main point here is that the robust version does what is expected. I think a more interesting question here, which sort of opens up a whole new sort of set of questions related to generalizability amongst other appropriate, like the design of appropriate metrics for learning with decision-dependent data. So we can see what's happening here as we scale, again, the size of the perturbation based on what we trained on. If the size of the perturbation is smaller than what we trained on, then of course, performative prediction actually does better than the robust version in terms of false positive rate. But as you increase the size of the perturbation, rapidly the performative prediction problem starts to, I mean, you might as well be flipping a coin at some point here, right? So, and it's even modest values of the scaling. While the robust version, definitely degrades, but not nearly as rapidly. Okay, so I'm about done here. And so I'll just wrap up and kind of give a summary of what's going on. So we started at the beginning with this central tenet of sort of present day machine learning that, in particular for supervised learning, that seems to fail to hold in a lot of learning-based intelligent systems, in particular intelligent systems or infrastructure systems where we're starting to introduce machine learning and other decision-making algorithms, automation. And so the question is, what should be sort of the next reasonable tenet for modern machine learning in these systems? And it's not totally clear to me yet what the answer is, but it is clear to me that game theoretic abstractions seem to be extremely key. So some of the observations we saw in today's talk is that you get arguably more interpretable equilibrium notions that are actually obtainable by first order methods, so simple things to implement. We can get better convergence properties in terms of provable convergence and sample efficiency. So the recent paper by Yu et al. Actually shows, as I mentioned, some really fast convergence, and some of those ideas can port over to the learning with decision-dependent data. And in essence, this game theoretic abstraction, and this is perhaps the most important point here, is that you're able to capture the environment's reaction to your decisions, even when you're sort of training in this like offline setting, right? Okay, so yeah, I won't go over these, but there's a fascinating number of open directions in terms of learning-based mechanism design, where we take into consideration things like moral hazard and adverse selection. And we didn't even start to scratch the surface on adding in state evolution or dynamics, which are also an inherent property of these large-scale systems. So I'll just sort of wrap up by coming back to this picture from the beginning. So we noted from this larger sort of market ecosystem that I described, where we have various layers in which algorithms are sort of interacting. And then we sort of are training each one of these in its own sort of feedback loop. And we focused on one particular problem here related to feedback-induced distributional shift. But really, there's a series of other interesting problems that come along with this, including how to deal with these highly non-convex landscapes. And I think there's been several talks in this series which are sort of targeting that problem. And then a whole nother problem is in how to test and evaluate these algorithms. And the way we're sort of doing it now is in an ad hoc way of pitting them against each other. And we end up getting these very complex game dynamics, including people discovering things like chaos, which is quite interesting. And this is something we don't quite understand. So I think there's a fascinating sort of new agenda here in terms of understanding how to analyze this market ecosystem in terms of training, evaluation, and deployment, as well as at the level of sort of the system, like once we deploy it in the real world, we have this sort of systems point of view. So I'll finish with that. I'm sorry I kind of went on a little too long.
Fantastic. A great talk, Lillian. Lillian, there are a couple of questions, and let me just sort of get to them. Let's get to the first question was Daryl Farber. Is there a way to relate back to your motivating examples and talk about what you might do? For example, it says, by the Uber driver's strategic behavior, which is one of your motivating examples.
Yeah, so I mean, in the context of the Uber drivers, I think that situation is much more nuanced, right? Because I mean, in what I described, we haven't really sort of captured, I mean, we've assumed that users are utility maximizers. And so I think this is actually an interesting question with regards to incorporating behavioral models. So actually models that actually capture how people make decisions in practice, such as, say, prospect theoretic utility functions. Yeah, so I think that it is a good question about how to capture that Uber driver model. But more generally, in terms of connecting back to the motivating examples, so I kind of glossed over it, but the last example where I was showing about the Portuguese bank data, that like this is actually I mean, I know it's in simulation, but the idea there is to capture that agents are being strategic about their features that are then being used to determine, for example, what is the interest rate that they will get on this fixed term deposit. So I don't know if that totally answers your question.
Yeah. Another wonderful question from John Barras. Welcome, John. Good enough, is what he says.
Okay.
So John's question is, from control theory, we know there's strong connections with games, robust control, large deviations, and maximum entropy stochastic control. We've understood these in very general settings and have shown that there are better models for robustness in machine learning. So what is your thoughts about whether these methods, how these have, whether these are ways to think about robustness in machine learning? And the second question is explicit knowledge of the metrics in their functional form.
Yeah, so I think that is one of the directions that maybe is a little bit glossed over in the style of talk that I was giving, but I think that there's a fundamental role for like connecting what has been done in classical robust control to what is being done now in modern machine learning. And there's several groups that are actually pushing in this direction. Yeah, so I think that, I mean, honestly, that's the right direction to go, is to try to leverage some of those insights and tools from robust control in the way that we think about machine learning. Yeah.
Let me pursue also your, the Seattle data also. So you're talking about this distributional shifts based on people, on people using what they do. So what is your sense about, if you're a city planner, what would you do to set parking rates in Seattle, sort of based on this kind of min-max style? How would you set that? I think you told me that nowadays the meter rates can be set by wireless and so on.
No, yeah, so not in Seattle. We're not quite at that point. But I think the first thing that I would try to do, so I mean, they're highly budget constrained here in Seattle, and I think this is true in many cities. So the first thing I would try to do is work with them to fix how they're collecting data so that it is not biased and that they can do it in an adaptive way. And that is something that we're doing with them. So they're now starting to rely more on models and letting us, use, for example, some pure expiration algorithms that we have to determine where they're going to collect the next data that's the most informative for improving these models. In terms of setting price, I think first we need to get an understanding of what is actually happening in terms of how people are consuming parking resources. And then maybe some new ideas will come for how to set the prices based on our understanding of how people use the system in the first place. I think right now we don't even have a good understanding of how people use the system. And what drives them.
There's a follow-up question from John, which is very good. I wish we had a format that people ask. So what is there? I think he's really on to John's answer. I was like, there's been a lot of work in stochastic control. And
yeah,
had a lot of rich dividend. So the question is, how do we harvest some of that into this robustifying machine learning?
Yeah, I completely agree that
this question.
Yeah, I completely agree that people aren't digging deep enough. I mean, I've had several conversations with Kevin Jameson here and some of his students in computer science who's working in this area. And I think that I don't know, maybe we need some venue to, or like a salon of some sort to review some of the older literature that's very useful. I mean, the stuff that I showed at the beginning for showing provable convergence with the timescale separation, that is extremely dependent on old singular perturbation literature. And I think if we hadn't been digging in the literature, we wouldn't have saw those results and been able to use them. So,
I think you may be onto something. Why don't you connect with John? And maybe it's a nice idea to think about a workshop. And,
yeah, I think that would be great.
That would be much needed by the community.
Yeah, I agree.
Yeah. Wonderful. I think you're really onto something. I must say, you're really, this is really a very, very interesting area. So
Yeah.
thank you so much for this wonderful talk, and we'll look forward to the follow-up that comes from this. So thank you once again, Lillian.
All right.
And
thanks for inviting me.
okay, bye-bye.